Everybody, and welcome back to AP Physics 2 for our fourth and final day of talking about optics. Today, we'll be talking about interference and diffraction, properties that are evidence of light's wave nature. As always, we'll start you off by going through the agenda first. We'll do a quick overview of the lesson, followed by our daily warm-up, where we look at the question that we finished with last lesson. Then we'll talk about everything that you need to know about diffraction, and then we'll work through some guided practice, some problems from the AP Physics question bank. We'll do a quick debrief and summary, make sure that you picked up what we were laying down, and then we'll do some AP exam practice, leave you with a little something for tomorrow. I'm Joe Mancino from Glastonbury High School in Glastonbury, Connecticut, and I'm excited to be with you again for this second week of physics.
And I'm Brendan Eaton from Reedy High School in Frisco, Texas, and looking forward to this lesson as well. So just a quick overview of what we're going to talk about today. We're going to talk about diffraction of light and discuss what evidence we have of the wave nature of light, conditions that cause a diffraction pattern, factors that affect spacing of what we call bright spots when we talk about diffraction patterns.
And when we're done talking about diffraction, we'll talk about something called thin film interference. We'll discuss how light interferes with itself in a thin film and how light interferes at a thin coating, which is a little bit different from a thin film.
And you should already know the terms frequency, velocity, and wavelength and how they interact with each other. And you should also know constructive and destructive interference.
So we're hoping that by the end of this lesson, you can determine whether or not light will diffract. You should also be able to predict how the wavelength, the slit spacing, and the distance to a screen affect a diffraction pattern. You should also have a sense of how you might measure something really small using diffraction. Finally, you should know about the minimum film thickness for constructive or destructive interference and also the same properties of a coating.
Some skills that we'll talk about is using representations and models to solve problems qualitatively and quantitatively. So being able to discuss things quality-wise and use numbers to describe it. We should be able to make predictions and claims about natural phenomena and connect those ideas across all the topics in AP Physics 2.
Okay, now it's time for a quick warm-up. We're going to start with where we left off last class. So I had hoped that you would take a screenshot of this one on Friday afternoon. The figures below show cross-sections of the top portion of a convex lens in air, and then the same lens in water. An incident ray was shown in both cases, and your job was to trace the ray as it passed through the lens and then exited back into the original medium. So on the screen are my solutions. A couple things to point out. The same basic shape is going on in both cases. The index of refraction for water is less than the index of refraction for glass. The index of refraction for air is less than the index of refraction for glass. So either way, when light leaves the first medium and goes into the glass, it's going to bend towards the normal. If you look at when the light exits the glass and goes back into its original medium, it's also that same downward bend. But you'll notice the bending on the right diagram is less than the bending on the left diagram because those n values are more similar. Water's around 1.3 and change, glass is around 1.6, air is just 1. So it's significantly different from glass. There'd be a lot more bending. And your second job was to describe how this would affect the focal length of the lens. Describe how the focal length and the position of the image would be affected by the lens being in air or water. Well, if you look at the image on the right side of your screen, the lens in the water, you'll notice that converging rays would converge at a further point that pushes the focal point of the lens back towards the right of your screen. All right. So here's your warm-up question today. We have two wave pulses approaching each other. A small positive pulse coming in from the left side of your screen and a large negative pulse coming in from the right side of your screen. Which of these images could represent the moment that those waves overlap and then maybe a moment after that? I'll give you a few seconds to take a look. So we spoke earlier about the idea of wave superposition, two waves adding up and having their amplitudes add up. Well, if the amplitude of the positive wave and the amplitude of that negative pulse were to add up, you would definitely notice this image. A slightly negative wave, the sum of their amplitudes. But remember, waves do several tricks. The first one is superposition. They add up their amplitudes. The next cool thing that waves do is they go through each other. So sometime later, that negative pulse is still moving in the leftwards direction. That positive pulse is still moving in the rightwards direction.
All right, so this is what you need to know from this lesson. The first thing is the idea of diffraction. And we know that light diffracts through an opening if the wavelength is just the right size. And the amount of diffraction also depends on its wavelength and the slit spacing in a small little diffraction gradient. The second thing that we're going to talk about today is thin films. Basically, light reflecting off of a very thin layer exhibits some type of interference. And you may have seen this before, maybe at a gas station or something, right as it had just rained. You can see this kind of colored coating across the top of the water puddles. And that's really kind of what we're going to talk about with thin films. The thickness of those thin films determines the nature of the interference. And we should also be able to calculate the wavelength of light traveling in that new material. Because really light's traveling through the oil, through the water, and then bounces back out. And we're going to get into more detail about that in just a little. Last thing that we're going to talk about here is thin coatings. And a coating's thickness and index of refraction determines how the interference is happening and when it reflects off of a coating. We'll show you some examples of that a little bit later.
The first thing that we're going to take a look at is the process of diffraction. Now, diffraction is definitely a waves-only property. So to talk about diffraction, we need to talk about this gentleman here, Thomas Young, born in 1773, known as the last man who knew everything. Thomas Young is famous for a few things. First of all, he proved, at least at the time, that Isaac Newton was wrong about light. He helped decipher the Rosetta Stone. He studied vision, he studied light, he studied solid mechanics, he studied energy, physiology, musical harmony, and Egyptology. You may have heard of him from the Young-Helmholtz theory of color vision, that we have three kinds of nerves for color if you took AP Psych. This guy was doing everything. See, one reason Newton thought light was a stream of particles was that it didn't display interference patterns. Newton's issue was he was looking on the wrong scale. Light is really, really small. Because the wavelength of light is so small, the interference patterns it makes are very small. But they're not so hard to observe. We can observe interference patterns in water. We can see the spots where water waves add up or subtract out, and we can see that pattern of high spots and low spots and the ripples between them. But if you send a red laser through a very small hole, you see ripples where you should just see a dot. If you send a red laser through a series of very closely spaced cross-hatched openings, you see a pattern like this. Just a moment. All right, we're good. If you send a laser through a very small opening, you see a pattern of circles like that. If you send it through a series of cross-hatched dots like that, you see that pattern come out the other end. But Diffraction only occurs if the wavelength of the incoming light is roughly as big as the hole that it travels through. And that means there should be about a factor of 10 relationship. So if visible light is 400 nanometers to 700 nanometers, somewhere in the middle, let's say 550 nanometers, that's about green light. 550 nanometers, green light would experience diffraction if it encountered an obstacle that was maybe 55 nanometers or 5,500 nanometers, but any bigger or smaller than that, and light wouldn't exhibit a diffraction pattern. So here's what we mean by diffraction pattern. This is what Thomas Young did. Thomas Young sent light into, so from the left side of your screen, you'll see light moving towards two small openings, like in a wall. If light were a particle, it would go through one or the other. Two very, very close slits, light would pick one. And on the other side of the wall, if we streamed enough particles of light there, we'd see two bright spots. But that's not what happens, is it, Mr. Eden?
That is not what happens at all. So light doesn't purely act as a particle like the hypothesis said. So if monochromatic light shines through those two small slits, what you actually get on the other side of the slit is exhibiting some sort of wave nature where we see parts of waves adding up and parts of waves subtracting out, just like we saw with the picture of the ripples in the water. And what we notice on the screen is we get little spots where the waves are added up, and that's a nice bright line. And where the spots are not adding up, there's a dark spot. So the bright lines where the waves are adding up, we call those things maxima. And where they don't add up and we see a dark spot, that's what we call a minima.
So those maxima, those maximum bright spots, they appear where the path difference is an even multiple of half a wavelength. Those of you who remember this from AP Physics 1, it's just like the diffraction of sound. Light works just like sound because in this situation, light is acting like a wave. Those minimums, they appear where the path difference is an odd multiple of half a wavelength. Okay, so I brought something to show you. Here we go. One moment, I'm going to switch to my document camera over here.
Did you bring your Jello again?
I may have brought the Jello again. All right, I think you see me and you're about to see the document camera now. No, you don't, huh?
Nope.
Mr. Eaton, do they see the document camera right now?
They do not see the document camera.
They do not see the document camera. That is very, that is a problem. How about now? We got a document camera. Great.
Jello.
Okay, everybody. This is a document camera hovering over some Jello. You can see the Jello. You can see my laser. Now, I have in my hand a diffraction card. If you look at my picture in the screen, this card has several holes in it. Each hole has slits that are more and more closely spaced. Slits that are 110 slits per inch, 195 slits per inch, all the way up to 5,000 slits per inch. If I shine the laser through the holes that are 5,000 slits per inch, that's a laser through nothing, no holes. That's a laser through holes that are spaced 5,000 slits per inch. So notice there are 3 dots. Well, here's what's really happening with the light. I'm going to put the diffraction grating right here at the bottom. You might be able to see that at the bottom of your screen. I'll shine a laser through that. And I think if you look closely, you can see that the laser is not just moving in a straight line. It's moving in several straight lines. It's spreading out. It's diffracting as it goes through the diffraction grating. One beam of light going through many closely spaced slits forms that diffraction pattern, that spread. So I'm going to switch it back to the presentation. And you fine folks should see Mr. Eaton taking you through an example of that spreading of light in now. All right, you should see on your screen two vertical white lines, one of which has some breaks in it. On the left side, those white lines have an opening spaced a distance d apart, and we shined into that opening a red laser with a characteristic wavelength. I think this laser says it is 600 and something nanometers. Fantastic, 650 nanometers. So we shine 650 nanometer light through there. Now, if Newton were right and light was solely composed of particles, some of the light would have gone through one slit, some of it would have gone through the other slit, and some of it would have just bounced off. But that is not what happened. That's not what you saw. What did you see? You saw this. You saw light spread out. And that only makes sense if light is acting like a wave. Patterns of bright and dark and bright and dark and bright and dark, that's just like patterns of high and low and high and low and high and low in a water wave. So to identify the characteristics of this wave, first off, you saw several beams of light. From my end, I could see one central beam, two beams on either side of that, and two more dimmer ones on the far side of that. I could see 5 beams. So the spacing between the bright beam and the farthest beam, we call m equals 2. We call the central dot m equals 0, the next one over m equals 1, and the next over m equals 2. We call the angle to those theta. So we have d, lambda, theta, and m.
All right, and so the equation that relates these to find the maximum minima is d sine theta is equal to mu lambda, where d is the distance in between the slits, as you saw in the diagram. Theta is the angle from the central beam to the next beam up, and lambda is obviously wavelength as usual. And as Mr. Mancino said, m is a special variable, and it's the number of the maxima or minima. So maxima, you'll notice, is a whole number. It's 0, that's the central beam. The next beam out is 1, next beam out's 2, next beam out's 3. That's where you see the bright spots. But for minima, where there's a dark spot, they are multiples of, I don't know, it looks like it's 0.5 and then 1.5, 2.5. Maybe it's multiples of 0.5.
That sounds about right to me. We're going to look at a typical numeric problem that you might see about a setup like this. So it says a double slit setup has a slit spacing of 1.5 millimeters, and there's a screen is set up 3.5 meters away from that double slit. And your job is to find the angle from the middle bright dot to the next one over. So m equals 1. Well, d sine theta equals m lambda. We plug in 1 for m and rearrange for theta. Plug in what you know, and out pops an answer. And that's not a very exciting question. In AP Physics 2, we try to ask better questions than this. So you may have solved these on homework sets or on some tests just to make sure that you're able to work the numbers, but far more important is that relationship. The idea that you know what's going on. The central bright dot to the next dot up is affected by the spacing of those slits, is affected by the wavelength of the light, is affected by the distance to the wall. So we have one more diagram to show you. If the angle is really small, we get to apply an approximation called appropriately the small angle approximation. If the angle is really small, the hypotenuse is roughly equal to L. I'll show you that one more time. Notice that L is the distance to the wall. But if the angle is small, L is approximately equal to the hypotenuse. So d sine theta becomes d opposite over hypotenuse. That's x over L. And if d times x over L equals m lambda, we can rearrange that for an expression that describes the spacing of those bright dots. X is m lambda L over d. So to find the distance between the maxes or mins, we just use x is m lambda L over d. where x is the distance between the maxes and the mins, and lambda is the wavelength, and L is the distance to the screen, and D is the distance between the slits. And that's great and all. Your job as a smart AP Physics 2 student is to be able to interpret this. What happens to x if? And it's your teacher's job to plug something in there. So we might talk about what happens to x if the wavelength decreases. What happens to x if the screen were further away? What happens to x if D is really small? Notice D lives in the denominator of that equation, so you know what happens if it gets small. Okay, this is the kind of question that you would see on a university physics homework. Mr. Eaton, do you feel like solving this one?
I really like math. I don't feel like solving this one.
Me neither. I even brought a calculator, and you know what? I don't want to solve it either. So guess what? We're not going to do it. Here's the deal, everybody. AP Physics 2 is not about crunching numbers and solving problems. AP Physics 2 is about relationships. The relationships define physics, not the numbers, not the calculations. You can do this. You can screenshot it if you want. I color-coded it. You can walk yourself through it. The real questions are these. What would happen to the angle of diffraction for light of a higher wavelength? That's a toughie.
And what's going to happen to the spacing of the bright dots if the slits are closer together?
Those are the kind of relationships that this course is about. So I really wanted to shine a bunch of lasers through a bunch of diffraction gratings, but I don't have a bunch of lasers with me. So here's what you would see if I had a purple laser and a green laser and a red laser and I was doing a diffraction experiment. Notice the purple laser, the one with the shortest wavelength, is the closest spaced together. The green laser with a middle wavelength is a little bit more spread out. And the red laser with a longer wavelength, like 650 nanometers compared to maybe the low 400s for the purple laser, the red laser is even more spread out. What I did do a little earlier was I shined my green laser through a diffraction grating, that 5,000 slit per inch grating, and I got the image that you see on the left side of your screen. You'll notice a central bright dot and then two more secondary bright dots. Then I did exactly the same thing through the same grating with my red laser. From the same height, with the same grating, at the same distance, everything was the same except for the wavelength. And when I put them on the screen, I made sure it was a 1-to-1 scale. Neither picture is zoomed any differently. And then I made sure to line up those central bright lines. What I'd like you to notice is that the green laser spreads out that much before the first two dots. But the red laser spreads out more for its dots. The red laser spreads out more because it has a longer wavelength. What's up with this one, Mr. Eaton?
That looks like it's going through a crosshatch kind of pattern. And just on immediate inspection, I see that the green dots are closer together and the red dots are further apart. And that must be because red has a longer wavelength and green has a shorter wavelength.
That's it in a nutshell. So when waves pass by an edge, they diffract into the shadow region beyond that edge. Just like you can hear around corners, but you can't really see around them very well because the size of that opening is all wrong. The wavelength of light is so small that you can't see around corners, but the wavelength of sound is so big that you can hear around corners. And water can bend around obstacles. Waves bend around obstacles. Waves exhibit diffraction exactly the way that particles don't. When you walk through a door, one of you walks through. There's not a bright, solid, substantial you and then insubstantial, diffracted yous walking off at every angle. That's not something particles can do. All right. So we've talked about diffraction. Next up is the idea of thin film interference. The next two slides are just a preview of what you're going to learn. Don't write this down, although I'm sure you have a notebook by now. It's only here so that you know what's important at the very end. These are the two slides that you're going to need to walk away with. They're not going to mean a lot right now, but I need to tell you, these are the ones. First of all, we're going to define the wavelength of light in a different medium. as a function of its wavelength in air and the index of refraction of the new medium. Then we're going to teach you some rules for how to treat different materials and the way that they interact with light. So those two images, this one and this one, are the ones that you need to walk away with.
All right, so we're going to start with when light's crossing a boundary between two materials. We kind of touched on that a little bit earlier in the lecture. So say water and oil or air and water, something like that. Some of the light reflects and some of the light is going to cross the boundary. And when that light's reflected, it can undergo what we call a phase change. And you probably remember from pre-cal or math somewhere around there that a phase change just means that the wave itself is going to flip. Now, if N2, the index of refraction for the second substance, is greater, you'll get a 180-degree phase shift, meaning that the wave just completely flips upside down. And what that means is when light in the air bounces off of glass, it does undergo a phase change. So as you see in the diagram, we have air on top of water, and we know that air has a smaller index of refraction than water does. Now, when light travels through the air and tries to pass into the water, the reflected light off the water undergoes a 180-degree phase shift because the water has a higher index of refraction than air.
The way I always explain phase shifts to my students is I tell them to count the highs and the lows in the waves. So leading into the water, I'm noticing high, low, high, continuing that pattern. I would expect another low. There's a crest right before the light wave hits the water. But instead of bouncing off as a trough, as a dip, as a low, the incoming light's high, low, high, and the reflected light bounces off high. That's a phase shift.
So notice on the next one where the light is trying to escape the water to go back into air, water has a higher index of refraction than air. And in this case, the light doesn't phase shift. So as Mr. Mancino was just saying, notice that as the light's traveling up to the left, right as it hits the interface in between those two substances, you have a trough. And as it reflects, you have a crest, just like you would normally expect. Now, this occurs when light passes through a very thin layer of material, such as a soap bubble or a film of oil, like we talked about earlier. That's the only time that you're going to see something like this. But several things do happen when you have incident light.
Some of it reflects off the top of the film and does change phase, but some of the light refracts into the film. It follows Snell's law. Some of that refracted light refracts out the other side. But some of the light that was trapped in the film reflects back out, undergoes no phase change, refracts out the other side. Now that's a lot to take in, and I don't expect you to get all that. A picture is worth 1,000 words, and honestly, that slide has about 1,000 words in it. So here it is with a picture. Here is incoming light going through a material that is very small relative to the light. Check out the wavelength of that green light. If that green light was 550 nanometers, that orange material is really quite thin. So some of the light is reflected off the top of this material, and notice there is a phase change. Crest, trough, crest, trough, crest, crest. Ooh. But some of the light refracts into the material following Snell's law. Of the light that goes in, some of it just refracts out. But a small portion of that light that is inside the material reflects again off the inner surface of the material. And that reflected light didn't undergo a phase change. So when it leaves, well, now we've got some interference. I'm going to fade out everything that you would not see reflected. So everything else that's happening in the light really is there, but just those two reflected beams are the ones that we're going to focus on. What I'd like you to look at is if you were to be looking at those rays, you have crests meeting troughs. For that wavelength of green light, that's an anti-glare coating. When that wavelength of light shines at that angle on that material, you would not see green light in that reflection. You would see not green. Mr. Eden? Take it away.
So I see everything except for green in that picture because I think the green is actually destructively interfering. So when some of those reflected rays add up constructively, those wavelengths are more intense, aka that color is more intense. So on the soap bubbles behind the text you see on the screen, I see purple, I see blue, I even see maybe a little bit of yellow. Those are the waves that are reflecting and they're adding up constructively, and I see them brighter. Well, some of them, when they add up destructively, like the previous example where we had destructive interference with the green waves that are reflected, some of those reflected waves are going to add up and they're interfering destructively, and they're just absent from that reflection. So on the soap bubbles, maybe the only green that you actually see is the green coming from the plants, and it's not because of the thin film interference.
So a typical AP problem involves finding the minimum thickness of a material that will result in either constructive or destructive interference for light of a given wavelength in air. Most of the time, the College Board would assume that the wave enters perpendicular to the film, so you don't have to worry about any weird trigonometry. The surface reflected wave, the one that bounces off the surface of the film, undergoes that 180-degree phase change, but for thin film, the inner reflected wave does not undergo a phase change. The total distance as the light travels through the material, bounces off the bottom and comes back up, that total distance is twice the film thickness. Just like as I wiggle my finger from the top to the bottom and then the bottom to the top, my finger has traveled double the distance of my window. The total distance traveled for destructive interference in a thin film has to be a multiple of an entire wavelength, so that when the light leaves the film after phase shifting, crests are lining up with troughs and troughs are lining up with crests. For constructive interference, for crests to line up with crests, the minimum thickness has to be an odd multiple of half a wavelength, and that's super weird. What I mean is it needs to be half a wavelength, or 3/2 of a wavelength, or 5/2 of a wavelength. Any of those situations would result in that wavelength constructively interfering itself. The reflection would look extra green.
All right, this brings us to talking about the wavelength of the film and that being different from the wavelength in the air. So notice the equation that we have here. We have N1 lambda 1, that's index of refraction of the first substance, and the wavelength of the light through that first substance has to equal the index of refraction for the second substance times the wavelength of the second substance.
Leaping lizards, Mr. Eden. We talked about that in our lesson about light changing speeds. It came right back.
Oh, huh. Well, that's why we only care about the path difference for the wavelength of the light inside of the film.
Oh, we knew that was coming.
So what that brings us to is lambda through the film has to equal lambda in the air over the index of refraction of the film. So
wait a minute, that's one of the slides we said they ought to write down.
Yeah, but where did the index of refraction for air go?
The index of refraction for air. Let me check the Wayback Machine. Oh, it's 1. The index of refraction for light and air is basically 1.000 something.
So it just falls out. There you go.
The take-home lesson about thin film interference. For destructive interference, when light goes through a thin film, the thickness of the film should be an odd multiple of a half wavelength. So maybe the thin film is 1/2 the wavelength of light in the film, or its thickness is equal to the wavelength of light in the film, or 4.5 times the wavelength of light in the film, some multiple of a half wavelength. For constructive interference, the thickness of the film would need to be an odd multiple of a quarter wavelength. So 0.25, 0.75, 1.25 times the wavelength of light in the film. There you go. Those will definitely not be given on an AP test or anything. Odds are good you probably have to remember those. If you'll be taking a test on this material in high school, you are going to want to take a screenshot of that. Hope you got it. So one last time, if you're a visual thinker like me, this to me speaks to me. So here's a quick question for you. 555 nanometer light, that's our green light again, is shining on a soap bubble with an index of refraction of 1.35. Can you calculate the minimum thickness needed for destructive interference? And I know your temptation is going to be to divide 555 by 2 and say, yeah, the minimum thickness is half the wavelength, doy, but you also need to recall that the wavelength in the film is different from the wavelength in air. The first part of your job is to calculate the wavelength of light inside that soap. So it's 555 nanometers divided by the index of refraction for the soap. So the wavelength of light in the soap is only 411 nanometers. So the minimum thickness of the soap bubble to destructively interfere with green light is 206 nanometers.
Okay, so if you have a thin film that is just on a surface that has a different index of refraction from what's on the other side, we call that thing a thin coating. And coatings are frequently used on glass lenses, kind of like sunglasses. You see people walking around with sunglasses with colored lenses from the outside, and you don't necessarily see that color when you're looking through them from the other. But another example of a thin coating is an oil slick, which is a thin layer of oil on top of water. And again, you've probably seen that at a gas station before, you know, right after it rains, a little bit of colored coating on top of the water. But if the surface of the coating rests on if the surface of the coating is resting on something that has a smaller end than I'm sorry, Mr. Mancino, what am I trying to say here? If the surface the coating
rests on has a smaller end value than the coating, the things are exactly the same as for a film. If light is going from low N to high N, back to low N, it works the same as a thin film, just like air, soap, air. Maybe it goes air, oil, glass, where the glass or the oil has a high index of refraction. But coatings work differently if the material of the coating has an intermediate N value. If the material of the coating has an N value between air and whatever it's coating, then it acts opposite how it does for a film. So my glasses, for example, the glass is, it has an index of refraction of 1.57. What a dork that I know that. Air has an index of refraction of 1. I know that the thin material covering my glasses to make them anti-glare glasses has an index of refraction between 1 of air and the 1.57 of my glasses. It doesn't act as a film, it acts as a coating. So thin coatings follow the opposite rules. Thin coatings work differently because that internally reflected ray for a thin coating does not undergo a phase change. So the same rules apply, except that they're flip-flopped. The 1/4 becomes a half and the half becomes a quarter. And odds are good that if you are taking this test in high school, you're going to want to memorize that too. But again, I'm a visual thinker, so I think of it this way. I think of this example. On the left side of your screen, you see an intermediate N value for that green material. It's higher than the N value of air and lower than the N value of glass. That works like a coating. On the right side, it's still a material that's coating glass, but the material has a higher N value than the thing it coats. So it works like a film. Here it all is in one screen. Screenshot that. That's the important one. And we're going to move on to some guided practice.
Right, guided practice. So in our guided practice, we're trying to answer 3 questions. The first question is about factors that affect the spacing of bright dots. Second is about thin films and coatings. And the third is about finding light's wavelength from a diffraction pattern. The first question, here we go. Okay, laser light passes through slit A and creates a diffraction pattern on the screen. The same color of light, AKA maybe the exact same laser, is then passed through slit B, and the new pattern has fringes, bright dots, that are more closely spaced than before. Which of the following could explain why the spacings are different on the screen?
I always like to narrow some of these down if I can, maybe cross something out that doesn't seem reasonable. Mr. Eden, is there anything here that just strikes you as maybe they're not a great answer?
I think the last two talk about the distance between the light source, and the slit. We never had any of that in our equation. So I don't think the last
that
two
even
are
matters.
reasonable at all. Yeah, those are bad. Those are bad. So that leaves us down to slit A is wider than slit B, or slit B is wider than slit A. So if I know it's the exact same light passing through both of the slits, and slit B has fringes that are closer together, that means that slit B has to be wider than slit A.
And there it is. So we said that we would talk about how to measure the width of a human hair, and you can do it with that equation. X equals m lambda L over D. If you have a laser of known wavelength, and you can get a three colors of lasers, they're very inexpensive. Get them shipped to your house. Get a red, get a blue, get a green. What else are you going to do? You're staying home. You can shine that laser across a single piece of hair. I can't. You can. You can shine it across a single piece of hair and measure. You'll see it for real. Dots on the opposite wall. Bright green dots lining your wall all in a row. Well, you know the distance to the hair and the wall. You know how far apart they are. You can count the number of dots. So you have X. You know lambda. You've measured L. You can count M. In fact, the only unknown is D, the width of your hair. All right. The next question is about the interference of light as it travels through a thin film. Now, the College Board doesn't always differentiate between thin films and thin coatings. They refer to everything as a film, and it's your job to figure out if it's acting like a film or acting like a coating. Well, in this scenario, the material that makes up the film has an index of refraction higher than the other two, so we know it acts like a film. And if it acts like a film, I'm going to zero your eyes in on the first word in the second to last line. It says constructive. Constructive interference, thin film, lambda over 4.
All right, last one. Monochromatic light shines through two slits a distance d apart. On a screen distance L away, two adjacent bright dots are separated by a distance x. What is the wavelength of the light? And for this problem, we can use our basic equation that we defined earlier, where x equals n lambda L over d.
This is another apology that I have to make. I used M earlier. The College Board uses N, but thank you, Mrs. Shear, for teaching me M.
I learned it as N also. So N equals 1 because the dots are adjacent to each other. Okay, so if I just simplify and take N out of the equation, you get lambda is equal to xd over L, where x is the spacing in between the dots, and d is the distance to the screen. And no, d is the slit width, and L is the distance to the screen. So there's no numerical solution to this. It's just symbolic.
Sometimes it's just algebra. All right, that does it for today. Time to talk you through what we learned and make sure that you get the key takeaways from today. First off, did you get that light diffracts if the wavelength is just right? If the wavelength is within a factor of 10 to the size of its obstacle? I hope so. Did you figure out that a thicker obstacle causes a narrower diffraction pattern, that a shorter wavelength causes a narrower diffraction pattern? Remember, the green diffracted less than the red did. Did you notice that light reflects off the outer and inner surfaces of the material, but undergoes a phase change if it reflects off a material with a higher N value? I hope so.
And can you do these things? Can you calculate the angle to a maximum or a minimum? Can you find the distance between bright spots in a diffraction pattern? Explain how diffraction is evidence of light's wave nature, and determine how particular wavelength will interfere with the film or encoding.
Okay, some quick AP exam practice. One question we're going to leave you with, and we'll take this one on first thing tomorrow. So grab a screenshot of this. It's coming back tomorrow. A boat is leaking a thin film of oil of n equals 1.5 on some water where n equals 1.3. In one area, looking at it, looks kind of green. Oil's not green, but it looks green. So specifically, I want to know, how does constructive interference contribute to the green appearance of that water? Well, thank you very much for joining us. We know that not everybody has access to the internet. College Board is working on solutions to get you what you need. If you or someone you know needs help with tools, needs help with connectivity, reach out to the College Board and let them know at cb.org/tech. It's a quick survey. You throw in your contact information and someone from College Board really will reach out to you and help you solve whatever questions you have. Pay attention for a big announcement coming out April 3rd with details for all of your AP exams. And of course, thanks for watching. We hope you join us again. Be sure to complete the practice question so that we can review the answer next lesson.